Welcome, everybody. Welcome again. We're glad to have you with us here. For the first VIRTEX Symposium, if you've been here for 3 minutes, you've already heard a lot of this, but we're going to start over again really quickly. Welcome. We're glad you're here. Everyone is welcome to enter questions or comments into the chat at any time. Unmute your microphone to ask questions during the panel Q&A sessions. You are welcome to share videos during the panel Q&A sessions. And so, program organizers, I'm Christine Shupla, and with me is Yolanda Ballard, and we are so glad to have all of you here with us today, our scientists and our clubs. Thank you so much for joining us. Yay! And here's our agenda one more time for today. We are just about to get started right now with our very first speaker. So our first three speakers, Dr. Pascal Lee is going to be talking first, and he studies Mars and geological evolution. He has a place up in the Arctic region where they study and practice things, and as well as in Antarctica. He's done so much exciting work, and we can't wait to hear from him. And then after him, we'll be hearing from Avery. Avery is a student who is studying astronomy, and she also works with the National Radio Astronomical Observatory. Really, really cool. And they have these places. They can't have radio observatories in the middle of a city because of all the radio waves. They have to be kind of far from the cities, which is pretty cool. And then our last speaker for the first session here is Dr. Alan Treeman, who will be speaking here in person. So I am going to stop sharing, and Dr. Pascal Lee, are you ready to begin?
Yes, ready to go. Good morning, everybody.
Good morning. Please, thank you so much. Please feel free to share your slides if you have any, and we're looking forward to hearing more.
Yep, I have about 7 minutes. Is that correct?
Yes, 7 minutes. Thank you.
Okay, so hi again, everybody. I'm going to talk to you about the NASA Halton Mars Project, HMP. It takes place every summer in the high Arctic on Devon Island. Devon Island is the largest uninhabited island on Earth. It's about the size of West Virginia or Croatia. Here is a map of where NASA often goes to do planetary analog work, the Southwest deserts of the US, Pavilion Lake in Canada. Devon Island is up there in the high Arctic. It's cold and dry. This is a map essentially of places that are extreme in one way or another in the direction of Mars. The Namib Desert is extremely sandy. Antarctica is extremely cold. The Atacama is extremely dry. The Altiplano is drenched in UV light. Hawaii is extremely pleasant. Devon Island is here. It's beyond the Arctic Circle. So when we're up there in the summer, the sun never sets. The main attraction on this island is Halton Crater. It's a meteorite impact crater that formed 23 million years ago. Here is the crater in its full glory, viewed from 10,000 feet of altitude looking towards the north. Of course, we don't exactly know how fast the impactor came in at. So the size of a crater depends on the energy of the impact. So as you know, 1/2 of mv squared. If v was high, m doesn't need to be that big. If m was large, then v doesn't need to be that big. So we figure that at 20 kilometers per second, the impactor was about 1 kilometer in size. I'm showing you the Eiffel Tower for scale. The Eiffel Tower, which of course normally is in Paris. And Halton Mars Project Research Station is there up on the northwestern rim of Halton Crater. That's our base camp. That's where we go every summer. Now, I should say that we could go in the winter, but of course the entire landscape is covered in snow at that point, so it loses its Mars analog attraction. But here's what the terrain looks like. And this might be reminiscent for you of the Viking landing sites or some of these other Mars landing sites that we visited. You should bear in mind that there's no vegetation whatsoever, at least not much that's visible. And so this is a big advantage. If you want to test a robot, for example, it doesn't have to recognize a plant which is quite challenging often for robots to do versus a rock. And so you have a terrain that's really analogous in that operational sense. Let me show you very quickly a set series of pairs of pictures with Mars on the left and Devon Island on the right. We won't have time to go into the geology of it all, but just want to give you a flavor of why this place is so incredible. So Devon Island and Mars can be compared for their craters. On Devon, you know the age of the crater, you know the size of it, you know how much weathering has been taking place. And then conversely, you can get a sense of how much weathering has taken place on Mars over the much longer and older age of these craters in some cases. And so you get a better sense of, you can constrain what the climate on Mars has done to erode its craters by having this calibrated example on Devon Island. But the terrain is laced with ground ice. We're in the Arctic. There's permafrost, which allows the ice to stay year round. So it results in patterned ground. You have rock glaciers on Mars, which are, we think, still rich in ice, but might be completely blanketed by rocks, and also with rocks embedded in them. But very similar glacial morphologies on Devon as well. Rock glaciers, where you have more rock than ice, those exist too on Devon. Sapping valleys, which are an unusual type of valley that grows towards the source. It's sort of the source eating its way into the virgin ground that allows these valleys to grow over time. That's a relatively rare occurrence on Earth, and of course we have those somehow on Devon Island. But there are also these valley networks, so intriguing on Mars, with parallels that were very difficult to find here on Earth until we found these beautiful ones on Devon Island. Turns out on Devon, they were formed underneath ice sheets and ice covers. And so this is sort of revising our thinking about how these valley networks might have formed on Mars. They might actually be indicative of a very cold climate early in Mars's history, not a warm one. And then you have canyons, amazing canyons, same size, same scale, very similar morphologies. These on Devon were formed by glaciers. Again, so you have this consistent story of ice having acted at the surface of Mars in ancient history, which might be telling you that the planet was once much more glaciated than it is today. So here are some of these tributary valleys of Valles Marineris, Eos Chasma on Mars, shown in profile on the top, and Devon Island's glacial trough valleys. This one, we call it Astronaut Canyon. You get to name a lot of things on Devon Island when you do geology there, because it's uninhabited, so nothing is named. And so it's a joy to be able to still do this. Gullies of type 1, we have them on Devon. Gullies of type 2, gullies of type 3, gullies of type 4. You're now a world expert on gullies. And you can see they have different implications, different types of processes taking place. Some result from surface glacial melting, others from snowpatch melting. These are from ground ice seepage. So a real diversity of gully types. And then you have RSLs, these very strange recurrent slope lineae, these streaks that you find on slopes. On Devon, they seem to be associated with microbial growth fed by seepage. Of course, on Mars, we don't know how they formed, but it's very intriguing that we have analogs, at least visually. And then you have the rocky desert terrain, which I just mentioned earlier. Here are some other examples. And then ancient impact crater lake beds on Devon Island and on Mars. We landed at Gale Crater at a place where, at Gusev Crater with the MER Spirit rover at this location that we think was an ancient lake bed inside a crater on Mars. Very similar to this landscape that we see on Devon.
Oh.
And of course, we're also learning how to explore Mars. So here's our base camp. You can learn how to operate a base, how to set it up, how to explore, what's best to use a team of 2, 3, 4 for your field exploration and excursions. We test robots, we test spacesuits. That's a whole discussion. Over the past 25 years, we've been trying to do one key thing, which is to reduce the mass of the spacesuit. Our current spacesuits weigh 300 pounds on Earth, And that's way too heavy. If you take that suit to the moon, but gravity is 6 times less, 300 pounds divided by 6, that's just 50 pounds. So it's bearable on your back. If you take, however, this 300-pound spacesuit to Mars, where gravity is 38% of the gravity on Earth, not 17 like on the moon, then the spacesuit has a felt weight of 125 pounds. So it's too heavy for you to do field work. And we have to trim the mass of the spacesuit in half, which is a huge challenge. So we're working on it. I won't have time to show you this movie, which itself is 7 minutes long, but you should feel free to check it out. It's on YouTube, Astronaut Smart Glove, and it gives you some aerial views of our site, plus some insights into the work we do.
Thank you so, so much, Dr. Lee. We appreciate it. Awesome. Woo! And Avery Abramson, I know you're online with us. Everyone hold your questions for Dr. Lee. Be thinking about questions that you have about his work, about what he does, about what's inspired him. Keep those in mind. Avery, can you go ahead and share your camera and maybe share your slides, or do you want us to share your slides?
I can share the slides.
Awesome. Thank you so much. Please, thank you.
All right. Hello, everyone. Thank you again, Dr. Supla, for the introduction earlier. I'm so excited to be here today to talk a little bit about my path. And this is my presentation for the symposium. So, a little bit about me. I'm originally from the Washington, D.C. area, and I'm currently going into my senior year at the University of Texas at Austin, where I pursue a major in astronomy and a minor in science communication. And then some fun facts about me are that my favorite color is pink, and I really enjoy songwriting as a hobby with my piano and my ukulele. So before I talk more about science, I wanted to talk about what inspired me to pursue astronomy. And if we go all the way back, when I was a little girl, my dad used to teach me about constellations. And the very first constellation that I learned about was the constellation Orion. And looking up at the sky, looking at these stars, I knew there was more to them than just little specks in the sky. So the next source of my inspiration was also visiting museums. And then at the bottom left, I have pictured the space shuttle at this museum called the Uvarhazy Museum, which was by my house. And I used to frequent that museum a lot with my family. And I also visited the Adler Planetarium, which is pictured in the top right. And then going to these museums, I got to learn more about astronomy and space science. And that really inspired me to pursue research through STEM opportunities. And during high school, I was able to participate in NASA programs that helped me gain exposure to space research. And through those programs, I experienced a talk like this one. I wanted to give a special shout out to Dr. Ed Murphy at the University of Virginia, where he talked about his career and astrobiology research. And that really showed me that pursuing astronomy was feasible and fun. So then I decided to commit to UT Austin and commit to a major in astronomy. And I wanted to talk about my path so far. So in high school, as I said, I was able to participate in NASA STEM programs. And pictured in the bottom left, that was my first science conference where I got to present my research about using satellite data to map mosquito populations and how they influence the spread of disease on Earth. And then in my freshman year of college, I was able to start astronomy research based on stellar astrophysics and space weather. And stellar astrophysics is basically studying how stars work, so like stellar mechanics. And I specifically studied a type of star called the white dwarf stars. And these stars are really cool because they can tell us a lot about the universe. One of my advisors was able to find out that the universe was around 14 billion years old because of the temperature of these stars. And white dwarf stars are basically the final stage of a star's life cycle. And because these are some of the oldest stars in the universe, we can correlate their age to that of the universe. And my research in space weather was basically studying how the sun and affects the environment around it, including the Earth. And I was also able to participate in a NASA program that let students design moon missions. And the one that I did was studying how magnetic interactions work on the moon. And then in my sophomore year, I started my favorite topic of research, which is galaxy evolution. And that's basically studying how galaxies grow and evolve over time. I specifically used data from this telescope in space called the James Webb Space Telescope. And what's really cool about this telescope is that it's able to look not only really far into space, but also way back in the past. So I look at galaxies that are not only super far, but super old. And I also got to participate in a mock astronaut mission, which I'll talk a little more about on the next slide. In my junior year, I continued my galaxy evolution research in Seoul in South Korea. And there it was really cool because I got to use space telescope data, but I also got to use computer simulations and compare the data from the computer simulations to what we see in space. I also got to do a communications internship for this astronomy magazine called Stardate Magazine, where I wrote articles about space science and astronomy for the McDonald Observatory in Texas. So this is a more fun part. I want to talk a little bit more about the unique environments I've done research in. The first one I wanted to talk about is pictured on the left, which is Mars. But Mars was actually just a desert in Utah in Hanksville. And the purpose of doing this was to simulate how research could be done once humans eventually reach Mars. So then at the Mars Desert Research Station, I worked with other physics and astronomy students from UT Austin to study space weather and white dwarf stars. And on the left, you can see me operating the solar telescope they had at their observatory site. And then on the right, I have pictures of where I currently am, which is the Green Bank Observatory. And what makes the Green Bank Observatory really cool, as Dr. Supla said earlier, is that it's in the National Radio Quiet Zone, which means there are very strict regulations on radio emissions. So to provide more context, you can't have cell towers. So that means you can't use your phone or your laptop with cellular internet. How I'm connected to you guys right now is actually through the wall. I'm connected via this thing called an Ethernet cable. And there are other things that are heavily regulated, such as microwaves. So we don't have a microwave in the houses that we live in. And if you do want a microwave, you have to put it in this thing called a Faraday cage so radio waves don't escape. And then another thing that's restricted are cars that use gasoline. If you're really close to the telescopes, you have to use cars that have diesel fuel. And another cool thing about this observatory is that it has this telescope called the Green Bank Telescope, which is the largest steerable radio telescope in the world. And you can see me and my advisor in front of it, and also me on top of the dish there. And here I continue my research on galaxy evolution. That concludes my presentation. Thank you so much for listening. If you're interested in similar activities, I have some QR codes for you here. If you want to come to Green Bank, there's a summer camp for 8th graders, which you can find out more about. But I'm happy to answer your questions during the Q&A session. Thank you so much.
Thank you so much, Avery. That was awesome. Woo! Wonderful, wonderful. And now we're going to open Dr. Treeman's presentation and share it. Hold on, I'm getting it loaded. I had to move it out of the way so we could see everyone else's. And let's see here. And then over. Should work.
Okay. Yeah. Hi, well, I'm Alan Treeman. I work here at the Lunar and Planetary Institute, and I work on a virtual extreme environment. It's clear that the slides have not transferred well from Mac to PC, but anyway, that's me. On the right side, of those of you that are here have probably been to the library, and that's our great globe collection in the library. And there I am levitating a globe of Mars. I was born in northern New Mexico. It's a top right slide there. Do I have a cursor? And it was in the mountains. And because of that, I was always really interested in rocks because they were everywhere around. And that's that ended up defining my career. So I started out being a geologist, an earth geologist. And like that first slide said, I sort of took a wrong turn somewhere and ended up doing planetary stuff. I've done a lot of field work in my life. I've been in some Arctic environments down here. I don't know if you can see the cursor or not, but the bottom left is me in Spitsbergen Island, which is north of Norway. And you can see bottom left is the toe of a glacier, and I'm standing on top of a little volcano there looking north toward the North Pole. So I've done field work on Earth. I also do other weird things. I write poems, which is the one in the middle. We have a conference and the abstracts for the conference are short, and I wrote the first one that was a haiku, so that's there. And what we do, my wife and I do for fun, is bird watching. And at the bottom right is an owl that has lived in our yard. It's been there for 3 years now and raised clutches of 4, 4, and 3 owlets. And so that's what we really like to do. Okay, but let's see. My extreme environment is roving on Mars. I work with the Mars rovers, both the Curiosity rover and the Perseverance rover. And Mars, as Pascal was saying, is very much a desert. If you've been in West Texas, the scene on the left could be pretty familiar, except there are no sagebrushes and no grasses and no creosotes or nothing. It's just rock and sand. And on the right side is a selfie picture of the Perseverance rover, which the rocks are really interesting, but if you're not interested in rocks, there's not much for you there. There's no life that we've found so far on it. And that's really the big thing that NASA is looking for in the Mars exploration are signs of life there, because as Pascal noted, that there are indications that Mars once had habitable environments. So Mars itself is a really difficult place, and I'm sorry the pictures on this slide have come out weird. Mars has no breathable air. The word "no" got lost somewhere in translation on there. There's no breathable air on Mars. It's all carbon dioxide, and it's so thin. It's like if you were in an airplane at like 40 or 50,000 feet up. It's just completely unbreathable. There's no water, no liquid water there. It's too cold for liquid water. There is some ice in the ground like Pascal was talking about. And on the right side is sort of the weather forecast for one of the days on our Perseverance rover. And you can see the rover and then its little helicopter to the left of it. That's the rightmost image, where the high that day was -8 Fahrenheit, which is really hard for anyone in Texas to understand. That's just, it's incredibly cold. And then the coldest is like -109 Fahrenheit, which I think that's been recorded once in Antarctica, that cold. But the highest temperatures you ever get on Mars are about room temperature here. That's the hottest it ever gets. Not in this room, not outside here in Texas, which is actually sort of a cool day for summer. So it's a pretty extreme environment. And that's where I spend my time. In fact, most of my time is spent at my desk doing a virtual field trip to doing extreme environments. So that's my life. What we're looking for on Mars are habitable environments. And what I'm showing here is where we are with the Perseverance rover. It's a river delta into an impact crater on Mars. And perhaps you can see the wiggles and straight lines in that river delta, and there's an impact crater in the middle of it. That was water flowed into that crater and deposited sediment, sand, and mud and rock into the crater, into a big lake there. And the best analogs on Earth are stuff like on the right side, the Yukon River Delta, where you can see the river meandering around as it wiggles down toward the ocean there. And of course, in the Earth one, we have all the green stuff, this life thing. And that's what we're looking for signs of on Mars so far, and have not yet found any, but we're looking hard. There's one possibility that's going to come out in a paper about a month and a half maybe from now. But mostly we've not found that. However, and I'm going to end up being weird like I always am. People look at the Mars images and think they see life things there. And if you wander around the internet, you can find all kinds of stuff like that. And on the bottom, on the top is it's a picture that was taken in Gale Crater, the Curiosity rover. And over on the right side, there's a funny little rock, and the blue line shows where that is and what it looks like blown up. And I looked at that and I thought, gosh, that looks like a vulture. But it's not, of course, it's just a rock. But it looks like a vulture. You have black vultures, I'm sure, down in Kingsville. We have them all over the place here too. But yeah, so we haven't yet found any bird life on Mars or anything, but we're looking. So that's my virtual environment. Okay, thank you.
It's time for our panel Q&A discussion. And so I am going to stop sharing those slides. And if you'd like, yeah, why don't you stay right here? And yep, somebody pointed out, Pascal pointed out, the rock even looks like a vulture on a tortoise. So that's pretty cool.
Yeah, it does.
For all of our clubs, if you have questions for any of our speakers, for Avery or for Pascal or for Alan here, you are welcome to enter them into the chat. For those of you in the room, you are welcome to come on up to the microphone, or we can bring a microphone to you. And if you would like us to unmute you, those of you online, so you can speak, please say something in the chat and we will unmute you so you can talk as well. So let's go ahead and get started with our Q&As. Who has a question?
Dr. Pascali, you mentioned the spacesuits weighing 300 pounds on Earth, and of course, cutting a whole bunch up in space. You mentioned 50 pounds. My question is, those 50 pounds, do they eventually, while they're up there, do they eventually feel those 50 pounds? Because 50 pounds on your back could get tiring after say 10, 15 minutes. So I want to know if they feel it and if they get tired.
Yeah, you're absolutely right. In fact, the Apollo spacesuit, which was actually used on the moon, weighed on Earth 220 pounds or so. And so when you wore it on the moon, it had a felt weight on your shoulders of about 40 pounds. And it's still tiring. And I think that's essentially why the heart rate of astronauts was going pretty high. I mean, aside from the fact that you're on the moon, of course, but it was manageable and they were productive. You can do field work. And if we lighten the spacesuit ultimately for Mars exploration, then it'll be all the more good for the moon. But the new spacesuit that's currently designed for the moon weighs 300 pounds on Earth. And that's because it's got more redundancies, more backups, more extra this and extra that. And it ends up being 100 pounds heavier, which is, of course, a bit crazy. On the moon, it will have a felt weight of about 50 pounds. And you're absolutely right. It's going to weigh on the astronauts and make their field work difficult. But on Mars, of course, it's complete. It rules out field work actually, because at 125 pounds of felt weight on Mars, you're not going to be productive at all. So the challenge is to cut the mass of the spacesuit in half. And so we want a spacesuit that on Earth will weigh about 150 pounds. So
Hello, can y'all hear us?
Yep. We want a spacesuit that on Earth will weigh about 150 pounds, so that by the time you take it to Mars, it will have a felt weight of about 60 pounds. And that's still, pretty challenging. The solution, I didn't have time to discuss that. The solution is to pair up your astronaut with an individual ATV. I don't know if you ride ATVs in the dirt and all that, but it's actually the solution is to spend most of your time on an ATV, so that you're not actually walking in your suit, you are actually just riding on a quad of sorts. And then You step off your vehicle just to pick up rocks with a much lighter spacesuit because it has less of the heavy things. The three most heavy things in a spacesuit are oxygen tanks, water tanks to cool you down, and batteries. So you carry most of the reserves of that on your ATV. You plug in while you're riding so that it recharges your spacesuit. And your spacesuit itself has smaller oxygen tanks, smaller water tanks, smaller batteries. So you no longer have a spacesuit that allows you to just walk for 8 hours like you had on the moon. It just allows you to walk around for 2 hours. But then your ATV stays very close to you. It's a smart rover. It follows you. And so the exploration unit essentially is no longer the astronaut plus the spacesuit. It's the astronaut plus the spacesuit plus his or her ATV. We think that's the solution.
Thank you. Thank you so much. So I know that one of the clubs tried to speak. Did somebody from that club have a question? If so, we can unmute. Plus, we have another question here in the room as well. So I'm going to let the one online. I think it was the club, Ramona Martinez's club. Is that right? Let's go to the question in the room, and then if anybody needs me to unmute you again, just let me know and I'll try to unmute you. Please go ahead. Yeah, go ahead and keep speaking. I think they can hear you even though, or is it turned on? Yeah, it's turned on. Just talk loudly.
Dr. Lee, I have another question for you. Other than the ATV, what are some other ways you've thought to lower the weight of the spacesuit?
Well, a few other things, new materials, essentially. But the ATV solution, I mean, it's such a drastic mass reduction that's needed. Meanwhile, the spacesuit is already so lean and mean. I mean, obviously, you know that a spacesuit is not just clothing. It's a whole wearable spacecraft. So it's got life support systems, waste disposal, communication systems, computers. It's a very complex piece of machinery. It's the minimalist spacecraft. So to cut the mass of that in half is easier said than done. And there's very, very little that you can really cut back on at this point without compromising the safety of the spacesuit. So the most promising solution is to offload the heavy stuff that you have essentially too much of when you're just doing a short spacewalk. Mm-hmm. And then you might use umbilicals as well. You know, if you're going to be parked somewhere for a while, like let's say you're at your base camp working on your rover, you got to repair it, you do some maintenance, and somehow that has to be done outdoors. Well, you're not going to keep hopping back onto your ATV to recharge your spacesuit. You're going to use an umbilical that feeds you your life support continuously so that you can work, you know, a few hours without having to recharge. So those are some solutions that we think will ultimately work.
Do we have somebody online who has a question now? You can enter it into the chat or you can unmute. I've just sent another invitation to unmute if you have a question for any of our three scientists. Let's go ahead and pass the microphone. We're looking for questions right now for either Avery or Alan, so that way they get a chance to answer some questions too. Go ahead and speak.
So when you're like on night plan, you always have to wear this. Always have to make sure you have make sure you always have to have. So when you're on space, you always make sure you have oxygen to breathe, because when you don't, you're gonna not breathe.
That's true. That's true.
No.
Very good. We always need to make sure if you are traveling someplace, particularly on another planet or maybe even high altitude, right? Somebody over here had a question for Alan. Yeah, last question for right now. We'll have another panel discussion in a little bit. Last question.
Have you ever tried bringing back ice or any other liquid related substances from Mars?
Yeah, the question is about bringing anything back from Mars. No, not yet. Our spacecraft so far have all been one-way trips. They land on the surface and die there, or are still going. The rover, the Perseverance rover, is collecting samples of rock and soil, which NASA might bring back, although they've sort of changed their mind this year, and we're not really sure what's going to happen. But yeah, I mean, it would be really nice to bring some ice back. Where Perseverance is right now, there isn't any ice in the subsurface. There isn't any ice to be found, but that's a really, really good thing, and it would be really important to bring back some of that ice, and maybe one of the future missions will do that. At the moment, the plans are just to bring back rock and soil and air, but ice would be a really great thing to bring back.
In just a couple minutes, we're going to have the presentation by the Boys and Girls Club of Kingsville. But first of all, let's go see if anyone online, some of you are online, anyone online have a question for Avery and about the National Radio Observatory or about the galaxies she studies, which are pretty far out. You can either enter it into the chat or you can maybe even raise your hand and I'll unmute you again. We have a question from here.
Yeah, hi Avery, this is Alan. I just saw some pictures on the news from the new Vera Rubin telescope that had some gravitational lensing. Can you talk just a bit about what that is?
Gravitational lensing?
Yeah.
I can try. So basically, I have to think about this. Uh, Light travel is supposed to travel in a straight line. But because there are fluctuations in like universe space-time, sometimes when we look out into space, that light does not travel in a straight line. And then that causes us to see what appears as like warped images of like galaxies. So if you look at, for example, like the James Webb Space Telescope has an image called the Deep Field image. And if you look at that, sometimes you'll see a galaxy that's kind of like curved weird. So like maybe a galaxy that like looks like a C, or it's like stretched out really thin. And that's not actually what the galaxy looks like. But because of gravitational lensing, you get that visual effect where that's what it looks like when you see it from Earth, or from the space telescopes. Does that make sense?
Yes, thank you. Thank you. Do you have a favorite galaxy, Avery?
Ooh, that's a good question. I really like the Pinwheel Galaxy. I think it's really pretty.
It is, absolutely. It's gorgeous. And we'll have to make sure we share a picture with everyone in the future of the Pinwheel Galaxy. It is amazing. Thank you to all of our first three speakers. Woo! And now it is time for the presentation by the Boys and Girls Club of Kingsville. They are going to be coming up here and speaking a couple at a time. And so who comes first? Who's up first? All right, for the two people who are coming up first, they're going to come up here and they're going to speak into the microphone right here.
Hello, my name is Mason, and I'm going to be a freshman in high school.
My name is Bo Berger.
So there are many similarities between Mars and Antofagasta de la Sierra or the Puna Desert, but there are also many differences.
We can't hear. I don't know if that's true for everybody.
And talk like this, okay? If you can hear it on there, then they can hear you.
So, Mars can get way colder
Oh, great.
temperatures because it's farther from the sun than Earth is. So the Puna Desert can't get that cold because it's limited by being on Earth. Mars has no signs of life yet, but the Puna Desert has microbial life. And Mars has volcanoes but no volcanic activity. But the Puna Desert has active volcanoes and some similar and have similar terrain. They both have high levels of UV rays and little to no.
Oh, some of y'all might be wondering. So some of y'all might be wondering, why even do this? Well, the reason why this even matters is because the science, because of the similarities on the Puna Desert or Antofagasta de la Sierra, the scientists have found potential for there to be life on Mars because there has been life found on the Puna Desert. Thank you.
So the students are coming up with portions of their presentation in pairs. So that's our next pair is right here. If you guys want to say hi or introduce.
Hello, my name is Ryder Lucas, and
Hi, I'm Zoe, and I'm going into 8th grade.
today we will be showing techniques for Mars.
And I'll be talking about safety and respectfulness.
But if I hold the microphone and you talk while you're holding up the thing, okay?
The first thing on the list is food and water because you need those to survive. Second of all, there's a flashlight in case it gets dark or there are dark crevices. A camera to take pictures of interesting things you find. A map to know where you are. Walkie-talkie to talk if you get lost and you need to talk to each other. A jacket in case it gets cold. Goggles to protect your eyes from dust and other things. Gloves to protect your hands, binoculars to see a far distance, and long pants to protect your legs.
And some things to keep us safe that we need to do is stick together, communicate, be cautious, no touching objects, watch footing, bring goggles and gloves. And things to show respect, we need to listen, eye contact, follow rules, don't litter, be patient, and respect culture and language.
And these are things that you learned during your project this year. Awesome, wonderful.
Extended thing of what we did a couple weeks ago. Well, actually, I don't know if it was that long ago, but yeah, we did a much smaller version of this, and we just did this again.
Wonderful, wonderful. Okay, and our next students here. Do you want to use the microphone or this microphone? Either way, you're going to need to be a little bit close to it, your preferences.
Hello everyone, my name is Addie and I'm going to the 6th grade.
Hello, everybody. My name is Amita, and I'm going to the 5th grade.
Hello, my name is Josh, and I'm going to the 6th grade.
Today we're going to be talking about one of our experiments, the touchdown lander. The touchdown lander represents astronauts safely landing on Mars. Following our scientific method, our first step was to gather the materials. The following materials were cups, eggs, tissue paper, plates, paper, straw, string, balloon, and
Based on the original, it crashed, so we made a prototype. And based off looking at the original that crashed, we improved it by using various items, and it was one of the favorite activities that we ever did. And these are the pictures of the stuff we did.
and thank you.
Beautiful, beautiful touchdown lander. Lots of gorgeous pictures. And do you want to use that microphone or this one?
Hello, my name is Elijah Solano. I'm going to 7th grade. So here are the facts about Mars. The heat, -degrees Fahrenheit, -60 degrees Celsius, which means cold, by the way. Dissection, it dissected terrains or the areas by the on the Martian surface by the pits and characterized. The atmosphere is the northern and southern, 1 to 2 kilometers. Atmosphere composed of carbon dioxide, 95.32% with small amounts of nitrogen.
One last group of presenters.
Hi, my name is Finnegan Lucas, and I will be going into the 8th grade. This is my partner,
Walter Kaiser, and I'm going into 6th.
Today we will be talking about 10 different jobs that we researched that work with NASA. The first 2 are an astronaut and an astrophysicist. 3, 4, and 5 are a rocket engineer, a launch director, and a computer engineer.
For number 6, we have a tour guide. 7, 8, 9, 10 are a security officer, administrator, a lunar specialist, and a mathematician.
Now that we have shared with you the different jobs that we have researched, we would like to share our career goals.
I would like to be a photographer because I've been interested in photography for a long time.
And I would like to be a science teacher, whether it be at a high school level or a college level. Thank you.
Wonderful, wonderful. All right. So that concludes the presentation by the club here. It is time for us to continue now with our next set of speakers. I'm going to go ahead and remind everyone what the schedule looks like or who's talking next. Let's go back to the PowerPoint here. Here, and let's do that. So our next few speakers, we have 3 more. Our next few speakers are going to be Dr. Maros Españolo, who I believe was the mentor for this club. Yes, and Laura Breitenfield and Willie Nicholas. Let's go ahead and Maro, would you like to share your own slides?
Yes, sure.
Okay, awesome. Thank you so much. Oh, you know what? I never shared what I was doing. Let me share that slide one more time so everybody can see the bios of our wonderful speakers who are about to talk. let me
Oh,
share that
sorry.
quickly, just for a second. Oh,
Yes.
no, never mind. You can start. That's fine. Thank you.
Okay. I go ahead. Go with this. Okay. Okay. Can you see the presentation and hear
We
me well?
can. We can see your beautiful slides. Thank you.
Okay. Thank you. Hi to everyone. My name is Mauro Spagnolo. There, I'm in Argentina right now. I live here in Argentina, and I work here. Yes. I was lucky to share this experience with Kingsville Club, and it was amazing. Uh, so let me talk about a bit about me. I'm a geologist also, um, and I started to be interested in planetary geology in particular by the end of my career. Mm, and then I did my PhD, and then I did a postdoc, and I finally have a had a position uh, here in the National Scientific Council. And right now I'm the lead of a small group that is called Laboratorio de Geología Planetaria, Planetary Geology Laboratory here in Buenos Aires. These beautiful people they are my students, Mara and Carolina. They are working on Mars, and Felipe who's working on meteorites, and I'm working in planetary geology, doing Martian geomorphology, and lunar works also. And with the Kingsville Club, we did a virtual field trip to the Puna Desert because unfortunately the time frame of the year to go there, we can't go. Well, we can go in winter, but it's very hard. So I show the club some pictures from early field trips. Here is also Kirby, uh, w- that is nice to see him because we went there together. And the Puna Desert, as the the kids, the students showed, it is another analog to Mars because of the dry climate, because of the high altitude, because of the volcanic landscapes. Uh, so it's a natural environment to study things, study the geology there, and so we can understand some processes on Mars. And what we do as geologists is go to the field, see things, take pictures, then gather a lot of data. And with that data, came back to our laboratory, do some computer modeling or analog modeling. Maybe the picture is not the best, but this white material you see here is dry ice, CO2 ice, and we are trying to make an experiment to simulate some geomorphologies we see on the pictures of Mars. And also with the club, I proposed the club to think that as if they were going to the field, uh, what they need to prepare before going, how can they conduct an experiment there, by taking pictures, making observations, and then what things they might take care of. And also with all this data, we, for example, in particular, we did some studies about wind ripples, mega ripples on the Puna. This is the left picture on the Puna Desert, and the right picture on Mars. They are very similar. We took the data there, and with that data, we came back to our laboratory. For example, we measure the height of these pictures. We made a cardboard model right there, and we put it inside a wind tunnel to simulate and understand how the wind can make these features or how they work. And also with our group here, we try to promote planetary geology and planetary sciences, and we try to make a lot of outreach. Here is a nice a nice room we have with a huge screen. You are seeing Mars there. There is the delta that Professor Alan talked about in crater Jezero. And sorry for that. There. And also, well, here I am talking with the students of Kingsville. This is part of the virtual field trip we did with slides and trying to answer some questions about the Puna Desert and Mars. And this is an example of the activity we did together with the club. So, and to finalize, I'm also very interested in arts. And let me stop presenting this. This is some things I do. I love sculpture. Oh, sorry. There. I show this because I think that science is very much like an art also, because you have to be creative, to ask questions, and to inspire other people. So thank you.
Thank you so much, Mauro. And thank you. Our next speaker is Laura. Would you like to share your slides?
Yes, I can.
Okay, thank you so much.
Okay, can you see my slides?
Look beautiful.
Great. Okay, hello everyone. My name is Laura. I am so glad to be with you here today. So I just wanted to first introduce myself. So I am at Stony Brook University and the Planetary Science Institute. And like our previous speakers, I am a scientist. So I am a planetary scientist, a geologist. I really agree with our previous speaker. I think science has a lot of overlap with art. And in my free time, I really like to do art. I love photography and I love painting. So that is something that I incorporate into my work, but also do on my free time. I wanted to tell you a little bit more about what kind of a scientist I am. So I study planetary science, and I specifically study rocks on other planets. So sometimes I'm looking at rocks here on Earth and then relating those to rocks on Mars, Venus, the moon, and asteroids. And I study these rocks by looking at the interaction between light and those rocks. So sometimes I'm shooting lasers at rocks, and other times I'm looking at how the light from the sun interacts with those rocks. I also use machine learning. So I'm sure you've heard of ChatGPT and other things like that. And so sometimes I'm using that machine learning to interpret rocks on other planets. Another thing I wanted to share with you today is a challenge that I have. So for me, I am dyslexic, and this makes it harder for me to read and write. So when I was your age, this was something that was very much affecting how I learn, and still to this day. And although that's a challenge I face, I think it also makes me a very visual thinker and a creative thinker. Okay, now I'm going to tell you a little bit about two extreme environments. So I study asteroids and I study the planet Venus. So these planetary bodies are really different from each other. Asteroids don't have atmospheres around them, whereas Venus has a very, very thick atmosphere, very high pressure at 92 bars, that is primarily composed of carbon dioxide. Additionally, these planetary bodies differ from each other in temperature. So the surfaces of asteroids are exposed to the vacuum of space, and so they're very, very cold. Whereas on the planet Venus, we have a very, very hot surface around 460 degrees Celsius. So I think these extreme environments in our solar system can also differ a lot from each other. So the way in which I study the extreme environment of asteroids is I take rocks and I put them into an asteroid chamber. So in the left image here, you can see this box, this metal box. And this is the asteroid chamber that I put sample rocks into. On the left, you can see in red, there's a pump. This pump takes the air out of the chamber, and so that we're under vacuum. And lastly, we pour into the top of the chamber liquid nitrogen, which is very, very cold, making this environment extreme, just like the surface of an asteroid. And then finally, behind this chamber, there's a spectrometer. And that spectrometer is an instrument that allows me to look at the interaction between light and those rocks and interpret the rock's composition. So this is the extreme environment of an asteroid. Similarly, and yet different, I do a very similar thing for the planet Venus. So on the right here, you can again see that I have a metal box. This metal box is a chamber that allows us to simulate the environment of the planet Venus. So again, I place rock samples in this chamber and I heat them up to very, very high temperatures, around 460 degrees Celsius. So although these chambers look really similar to each other, we can simulate the extreme environments of the asteroids as well as the planet Venus. So I just wanted to finish today by saying that it is my belief that science is for everyone. Science is around us in our everyday. And so I think being a curious person and figuring out how things work in our world is really important. And whether you're interested in art or math or writing, there are lots of different paths that can connect you to science in our world. So thank you very much for having me. It was great to talk to you.
Awesome. Wonderful. Thank you so, so much. Okay. And our next speaker in this session is Willie Nicholas. Willie, come on up and I will open up your slides and then you can introduce yourself. Let's see here. And yeah, too many choices on how to open the presentation. And then let me make sure it's going to share it as well. Is it opening it? Where did it go? Okay. And let me go ahead and I'm going to share this in the power. Where go? Let's share that. Share. That's okay. No worries here. I will let you play with it from here.
Okay. So hi, everyone. My name's Willie. I'm a staff scientist here at LPI. I just started here back in April, so it's all very exciting. And it's cool that we do stuff like this. I didn't know when I got this job that we do stuff like this, sort of outreach stuff. And basically what I do is I study volcanic rocks. I study volcanic rocks in a hands-on way. I've been all over the world studying volcanic rocks. Here, I'm gonna scroll down. Hopefully this works. And here at LPI, I'm mainly focused on rocks on other planets. But in the past, I've done quite a bit of work on volcanic rocks in a wide variety of places in the world. This is 2.8 billion year old. Oh, no, I'll just talk over here. Sorry. At a place called Kumo Greenstone Belt in eastern Finland, where they're some of the oldest volcanic rocks in the world. They don't really look like a normal volcano anymore. They're very, very weathered down. And I did a bunch of work on them. I analyzed their chemistry. I determined basically how they formed, when they formed, all these sorts of things. And then another place that I worked on Earth was there's this island called Gorgona Island, which is off the west coast of Colombia. It's a very sort of rural and formally dangerous area. They had a civil war there recently, but we were some of the first geologists. There I am. I've lost some weight since then. And that was a couple years ago. And we did some sampling there, and that was some very extreme sampling. We were in a jungle. There were monkeys, there were bats, there were snakes. If anyone here speaks Spanish, Isla Gorgona means like island of the Gorgons, like Medusa. Like it's a horrible snake island. It's full of snakes all the time. But it has very interesting rocks. But after that, after my time on the horrible snake island, I decided to study meteorites because meteorites are inside and don't have snakes. So I really got into meteorites after that. And these are two specific samples that I've worked on in the past. On the left is Ergchek 002. And for Ergchek is the oldest crustal rock in our solar system. People today have been talking a lot about other planets that we know, like Mars and Venus, but we had a first generation of planets that kind of formed in our early solar system, and then they all hit each other and got ripped apart in the early solar system to turn into new planets. Ergchek is from one of this first generation of planets, and it's the oldest rock we've ever dated, and we were one of the first people to date it. It was found in the Sahara Desert at a place called Ergchek. Meteorites are named after where you find them. So like in Algeria in May 2020. So like we as scientists took a while to analyze this rock because May 2020 was a wild time for all of us. I'm sure many of you remember. And so Ergchek is one of the oldest meteorites in the solar system. We actually just got this. I only got pieces of it. It's kind of hard to get a hold of. That's another meteorite that was also found at a place in the Sahara Desert, and it's one of the oldest rocks in the solar system, and from this first generation of planetesimals. That one has a really weird mineral in it called potassium feldspar that formerly was only found on Earth. It's bright pink. You can see that that's bright pink. It's very unusual for a meteorite. And on the right is Northwest Africa 3151, which is a braconite. It's a type of meteorite that comes from the asteroid belt. That one's not as early, but it still comes from an asteroid somewhere in the asteroid belt, and we're not entirely sure what that asteroid is. But we have braconites, and we study them chemically, how they form. Moving on a little. I've also worked a bunch on Martian meteorites. I wasn't here for the whole session this morning, so I don't know if anyone's brought this up before, but we have samples of the moon. Like we went to the moon, we had the Apollo missions, we all know about this. But we've never been to Mars. Humans have never been to Mars. We've never taken rocks back from Mars. We've never had sample return. Mars is way, way further. It's way harder to get to Mars. What we do have is something called Martian meteorites. So we know kind of vaguely what the chemistry of Mars is because we've sent rovers there and we've measured it. And we've been finding samples that fell from the sky all over the world that look like Mars. And we can analyze them a lot more accurately here on Earth. And these are Martian meteorites. There's about 200-ish of them. And this is Dar al Ghani 476. It's from Oman in the desert. It's another sample we've worked on that I've worked a bunch on Martian meteorites, just looking at their volcanic rocks, how they formed, their chemistry, and how they evolved, and what they can tell us about Mars. And this is me back in 2015. I was trying to find you guys more lab pictures. I think I just don't take pictures of myself in the lab. I've worked in the lab a lot, I promise. But this is me working with one of my main instruments that I work on with meteorites, which is called laser ablation. I shoot little lasers at meteorites, and they tell us what the composition of various meteorites are. But yeah, I think later today, you're probably going to do some tours of things around here. Okay, y'all are going to see the library list. Okay, cool. So there's a lot of stuff around here. There's a lot of resources down in Houston and there's a lot of meteorites. Your government, the government we all pay taxes to, like collects meteorites and we can study them. And that's the main thing I do is I look at meteorites that our government has collected that either fell here in the US, like there's one of the most famous Martian meteorites is called Los Angeles because it's from Los Angeles. So that's obvious. That's the property of the US government because it's from LA. But there's plenty of meteorites here in Texas, but the government also acquires pieces of Mars for scientists to study from places like Oman, as you see here. But yeah, if you have any questions.
And so now we're going to do our next panel Q&A session. So I'm going to stop sharing that. And so I want to remind people, those of you online, yes, Kirby, you'll be welcome to share your own slides at your turn. That would be awesome. We would love that. So those of you online, do you have questions for Mauro or for Laura or for Willie here? If you do, you are welcome to enter them in the chat, or if you can somehow signal to me that I'll send out an invitation for you to unmute. Well, it's not letting me do that anymore. I think I've done it too many times and now it's no longer doing that. But if you'd like to unmute, you are welcome to unmute and we'll try to figure out how to make that happen to ask a question, or you can enter it in the chat. Those of you here in the room, do you have questions for any of these three speakers, for Laura or for Mauro or for Willie? Give everybody a little bit of time to think here. So many awesome things. Yes, we do right there. Do you want to come up to the microphone or do you want me to bring the microphone to you? Come on up. Wonderful. Come on up. Speak right into here.
So you talked about the oldest microphone, the oldest meteorite you found, but what was like the newest one you found so far?
So the newest one we found are actually from Mars. So most meteorites are very old. They're 4.5 billion years, and a billion is 1,000 times a million. But the most recent one is around 180 million, which is young by geology standards. And those are from Mars. All of the youngest ones are from Mars because most of the other bodies in the solar system don't have volcanoes on them anymore. They've cooled too much, but Mars still does. Mars is pretty big. So all the young ones are Martian.
Laura, what's your favorite part of your job? When, day to day, week to week, month to month, what is the favorite thing that you get to do?
Yeah, I really love teaching people. So I really enjoy working with students and hearing about their interests. And, I think we all have different interests. And so if I can tailor what we're talking about or what we're researching to somebody's interest, that can be really, really fun. And then I would say the second part is getting into lab. So, I'm in the lab most days, and it's always interesting to collect new data and learn new information from these rocks.
Thank you. Did I see another hand? Anybody else here in the room? Do you want to come on down and ask a question? We've got another question here in the room. Which of our scientists is the question for? Is it for Mauro or for Laura or for Willie? Mauro. Okay, come on over.
What would be the best advice you would give to someone?
Someone who's interested in working like he does, or?
Like someone who is starting as a scientist, like what would be the best advice that you would give them?
Oh, that's a hard one. um, my best advice, I think, would be that's a lot of pressure. No, I think stay stay open mind. I think it's kind of cliche, but think out of the box. I mean, when you're starting as a scientist, one might be a bit overwhelming, that might think, oh, I read a lot of things. Would I be able to do this kind of studies? And so my advice would be that try to think out of the box all the time. Try to, as I mentioned, and I agree with Laura, to 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 think science as an art, in a sense that you have to resolve problems. So, but not only resolve questions, you have to learn how to ask those questions. So to learn how to ask questions, you have to, one needs like a creative mind. And I know that can sound a bit bad, because you say, oh, but I don't have a creative mind. No, but you can train that. And so I think my best advice would be, do what you like, pursue what you like, uh, uh, and never stop, or never think that you won't get, or you won't reach your what you're pursuing or what you want to pursue. Because there will be maybe more hard work for some people, some less work for another people, but if you really like what you do, you will reach it.
Absolutely, absolutely. It's all of those things are wonderful, and we can talk some more about that soon, about the role that creativity and perseverance, keep trying, play in science. And thank you, Mauro. Thank you so much to all of you. We're going to move on now to our last three speakers. I am going to share PowerPoint here, just to remind who our final three speakers are. We've got Dr. Kirby Runyon and Dr. Sumitra and Dr. Ari. Kirby, you are welcome to share your slides. I'm going to give everybody a couple seconds here to look at this so they can read everyone's wonderful bios. And then I'm going to stop sharing here. And I am going to invite you to share your slides and take it away.
Okay, great. Can you all hear me okay?
We can hear you great. Thank
Great.
you.
Well, first, before I share my slides, I want to give a shout out to Mauro, to Dr. Spaniolo. We were in the field in Argentina together where we picked up some really amazing rocks, very similar to what's on Mars. This is two rocks fused together. Mauro, do you recognize this?
Oh yes, I remember that.
So they're
Lovely.
very different types of volcanic rocks. One is called an ignimbrite. It's when a lot of hot volcanic ash welded itself together, and the other one is called basalt, which is kind of like what we have in Hawaii all over the place. So, but Mauro and I were in a very Mars-like terrain in Northwest Argentina. But that's not what I'm talking about today. I'm going to be talking about the extreme environment that I work on, which is reduced gravity. But before I get into that, I just want to tell you a little bit about myself. I'm a lifelong space nerd. I've loved space my whole life. And since high school, a little bit older than a lot of you students, I made it a goal to go to graduate school and get a PhD, a doctorate. And that was a goal I had from high school onward. And I succeeded in that, I'm very proud to say, but there were a lot of challenges along the way. I live in Washington, D.C. I'm married. I have a cat named Nixie that's named after Nix, which is one of the small moons of the planet Pluto. And yes, I'm one of those people who still thinks that Pluto's a planet. And and I love hanging out with friends. I volunteer in my church. My wife and I love to hang out with friends and kind of foster community here in DC and also up the road in Baltimore. But I'll go ahead and share my screen now. Let's see. Can you see this? Okay, great. I can't see any of the participants, so I'll go on. But I'm going to be talking about about impact craters. This is when meteorites hit the surfaces of other planets and dig these big holes in the ground we call craters, or more specifically, impact craters. On the left is a picture from Mars, from the Mars rover Opportunity, and this is a fairly small crater. It's maybe 3 meters or 30 feet, maybe 10 meters across. You'll see there's lots of rocks thrown out outside the crater. That stuff is called ejecta because it got ejected out of that hole in the ground. The picture on the right is of the moon, and if you have binoculars or a telescope, or if you know exactly where to look, you can just use your eye looking up at the moon. That's the crater Aristarchus, and it's about 30 kilometers, roughly, I think, across, or about 20 miles, roughly. And that was formed when an asteroid hit the moon. And so, most of the craters that we study around the solar system, they happened a long time ago. They happened, in some cases, billions of years ago, or maybe 100 million years ago, or tens or a few million years ago. So it's hard to watch craters actually form. And so that means that we have to go into the laboratory and we've got to make our own craters if we want to learn how craters form. And so this video that's looping right here is taken at a NASA facility called the NASA Ames Vertical Gun Range outside of San Francisco, California. And it's literally an artificial meteorite that shot at about 4 miles per second into a bucket of sand, and we can study how craters form. And then the stuff that's coming out is the ejecta, the stuff that gets kicked out of that crater. Now, when we make craters on Earth, they're formed in Earth gravity, but Earth has the most surface gravity of any solid world in the solar system. The craters on the moon, they formed in a lot less gravity. They formed in only 1/6 the gravity of Earth. If a kid weighed 100 pounds on Earth, they'd only weigh 17 pounds on the moon. Dr. Lee, Pascal Lee, talked about how 220-pound spacesuits weighed less than 50 pounds on the moon. And so cratering has to happen in less gravity when it happens on the moon, or if it happens on Mars, it's happening at only 2/5 the gravity of Earth. Here's video from the Apollo program. That's astronaut geologist Dr. Jack Schmidt bouncing around in moon gravity. So in order to recreate moon gravity on Earth, we have to go in a special airplane. This airplane is called G-Force One. It's run by a company called Zero G. And it's a modified Boeing 727. Right now, I'm dressed in the flight suit that we have to wear when we're on board the airplane. And this airplane flies at normal altitudes. If you've flown in a commercial airplane, you fly at about 35,000 feet. And that's the altitude that this airplane flies at as well, except that it varies its altitude between about 25 and 35,000 feet. And it does a bunch of steep climbs and steep descents, about 45 degrees up and 45 degrees down. And during about 20 seconds, while it's going over the top of this invisible hill in the sky, you have reduced gravity. You can do zero gravity. You can do moon gravity, 17% or 1/6. You can do Mars gravity, 2/5 or 38% the gravity of Earth. And this forklift here actually lifts up experiments that we do. And I study impact cratering, and we lifted our experiment into the cargo door of the airplane so that we could use reduced gravity. Here's what it looks like with zero gravity. That's me right here. Zero gravity, And so we do that 30 times in a row. On our flights, we do 10 that are Mars gravity, 2/5 the gravity, 10 that are moon gravity, 1/6 the gravity, and 10 that are zero gravity. And so that was a zero gravity parabola. And this is a box that contains our impact cratering experiment. Now this view, I'm just shooting this video on my phone. This is my friend Khan, and we're operating a catapult. And actually this catapult like a baking pan, like a brownie pan. We probably bought at Target or something. And we're simulating the stuff that ejecta that gets dug out of craters. And what we're using for that is sidewalk chalk. I just bought a bunch of colored sidewalk chalk on Amazon, and then I took a hammer and I just busted it up. And this is outside the airport hangar before we flew. And then we load it on the catapult to simulate a portion of that ejecta that comes out of the crater. Now, this is a moon gravity shot here. And so you're going to see the particles kind of, they don't look like they would look like on Earth. So I'm going to play it. But then the camera pans to the back of the airplane where my friend and colleague, Dr. George Pantelos, who studies how surgery happens in space, he's in a purple shirt and he's playing the djembe drums. So he's just being funny. His students are off doing the hard work and he's just playing the drums in moon gravity. So take a look. Chalk on the catapult, push over, and gravity push over. Pushing over. Fire that.
George, give me another bounce.
Then I do a backflip. And so that's a little bit of the extreme environment I get to work in for my science. Here's another video of what it's like to pour water on the moon. You can imagine astronauts on the moon in a future lunar habitat. They're inside. They don't have to wear a spacesuit when they're inside, but they're pouring a beverage for themselves. Well, if you've ever heard of surface tension, when you take chemistry or physical science, you might hear about something called hydrogen bonding. And hydrogen bonding is what leads to water sort of sticking to itself and sort of forming a thin skin on the surface of water. And this is what water bugs use to be able to walk and scoot on the top of the water in a lake or a stream without sinking. But surface tension, it's more pronounced, it's more noticeable in reduced gravity because the weight of the water doesn't matter as much. And so you're going to see me pouring water from this top bottle into the lower bottle in the extreme environment of moon gravity. And you'll see that it's kind of like pouring ketchup. So I'm going to go ahead and play this. It just sort of globs together. See, it's just these globs. I literally have to shake it like it's a bottle of ketchup to get it to come out. I'll play it again right there. Okay. That's the end of my prepared slides. But I'd be happy to either just how many more minutes do I have? I can riff.
We've been running a little bit behind,
Okay.
but if there's anything that you particularly want to share, absolutely do that. And otherwise, during the Q&A session after the next two speakers, we'd love to have you talk more.
Okay, we'll recoup some of the time. I'll pause right there and I'll be back for the panel.
Okay, thank you so much. And everyone keep in mind, yes, everyone keep in mind the questions that you might have for Dr. Kirby. Sumitra, so this is about extreme environments in many ways, and Sumitra lives and works in an extreme environment and is coming to us from Alaska. Would you like to go ahead? Do you want to share your slides?
Yeah, sure, I can share my slides.
Thank you so much.
Can everyone see my slides now? Hopefully.
We're seeing the
sorry.
presenter's view. So if you click on display settings, you can switch it up at the top where it says display settings.
Oh.
Yeah, if you can switch it so that way it's, yeah, swap them and then we'll see that. Perfect. Awesome.
All right, sorry. I think my presentation can hopefully get us back in track. Before I start, I just got back from my field work just like 12 hours ago, less than 12 hours ago. So still a bit sleepy, still a bit tired from that, but yeah. So I'm a PhD student over here in Alaska, Fairbanks, Alaska, and I'm studying how the permafrost is affecting the landscape here. And I do that using both field measurements and also using remote sensing. So satellites, I use that. So a bit about myself. So I came here in Alaska like just before the pandemic, like January 2020. When I got out of the airport, it was -41, and I was happy because it was like, okay, this is the coldest temperature to be, so it only gets warmer, right? I was wrong last year, so it did get colder. But yeah, it was a good fun for me. Like before I came to Alaska, I did my diploma in India, and then I was for almost 8 years in the UK doing my undergraduate, my master's, and a brief stint back home in India, and then I came here to Alaska. And in Alaska, I'm in the Geophysical Institute, the GI, as we call it. And then I study like soils. That's what I kind of do. And I look for how the soils are changing. And a lot of that involves kind of, as you can see, the bottom right picture is kind of showing, well, that's one of my advisors, Simon Zubak. I'm showing him and making sure what I'm analyzing is correct. And it's usually not that correct. So I'm always changing. So yeah, so where do I do my field work? So this is where I was just a couple of hours ago. So if you see the study area right on the top, it says study area. That's the Tulik field station. And on the right side, that's the image that we got from last year in around like end of April, early May. So we stay at this very beautiful campground, like field site called the Tulik field station. And then all the three sites on the left side, that's where we go and collect data, which involves GPS data, like ground measurements, soil temperatures. We collect soils as well to analyze how much ice there is, and various other things to just see how the landscape is changing. And I mentioned permafrost, but didn't really go into detail what it is. So permafrost here, it's all over in Alaska, and also in most of the Arctic as well. And that, so permafrost can be defined as anything that stays frozen for at least 2 years. So that can be water, but not always water. And it's any rock material, soil, or anything that stays frozen for at least 2 years. And what we are interested in is the water in the permafrost, because that's when that water goes, it creates subsidence or depressions. So I'll show you some of these pictures and videos. So on the first image on the left, you see the house kind of being just fallen into the ground. And the middle picture, that's just outside our offices. You see the white stuff like in the ground, that's ice. That's a lot of ice that was there. And when that ice slowly melted away, it created this giant sinkhole right on close to campus. And then on the right side image, there's also that this is one of the coastal regions here up in Alaska. So when the subsidence happens on the coast, it creates these. So we start to lose coastlines, and it creates like a lot of havoc to the coastal communities here in Alaska. And I can show. So this another the bottom left image is another image that was also again right outside our office 2 years ago. It started off with this, like I'll show you the video. It started with this small little sinkhole, and you can see the water kind of gushing through inside it. And the next morning, it created this giant. So it's just like less than 6 hours, and this giant sinkhole came in because all the water found a way to escape somewhere. So yeah, this is how the landscape here in Alaska is changing. So this is why scientists like me and others kind of are trying to study it, analyze it, and then find the solutions, like what can you do to prevent it from happening. Because also in permafrost, there's the amount of carbon that's there in the atmosphere right now, there's much more than that stored currently in the permafrost. So once that gets released, it'll be even more warmer. So I didn't really have too much to show, but like these are the people involved in the fieldwork. So two of my advisors, Simon Zwieback, Dr. Franz Meyer, both are scientists for ASF, Alaska Satellite Facility. And that's me holding the soil. So I'll talk a little bit about kind of like so I was telling you about all these processes that I'm doing. So the remote sensing I didn't talk about. So we do fieldwork, like fieldwork is the most accurate data that we can do, but we can only go to a few sites. We can't do the whole of Alaska because it's so remote already. So this is when remote sensing or satellites come into factor. So when we do remote sensing, when we get the accurate data, we kind of calibrate it to the satellite data that we can get, because satellite will cover a very large footprint of the Earth. So, but that is also an estimate. So with our fieldwork data, we make sure the estimate is correct with the satellites. And then we use the satellite data to kind of map the whole of Alaska. And then with that, we can see how much of Alaska is changing based on the permafrost and what's happening everywhere else. So yeah, that's a little bit about myself. And I would like to end just over here. This is a cue of all the stuff that we do. We also see these. Actually, these are muskox. We had a muskox in our first day in our field set, so we had to stop working for some time until they kind of slowly went away. They had just babies as well, so we had to stay away from them just for a few minutes. But yeah, this video, I like it because this one of the males just got up and just started hit his brother. So I kind of use this analogy saying that science is disruptive. You should be causing disturbance to kind of create new science. Thank you.
Thank you. Thank you. Wow. Those are some big animals. I don't know if I'd want to get too close to them. Thank you. So our last speaker for this morning is Ari. Ari, is it Kopel? I don't want to mispronounce anyone's name, and I'm probably sure I've done that for several of you. Ari?
It's Kopel. Thanks.
Kopel. Ari, would you like to share your own slides, or?
Yes,
Okay.
I will do that momentarily.
Thank you.
Okay, is that coming through okay?
Yep, we can see them perfectly. Thank you.
Awesome. Well, hi, everyone. It's great to be here with you virtually. My name's Ari Kopel. I'm a postdoctoral researcher and lecturer at Dartmouth College, which is in New Hampshire. And I do a lot of research that's funded by NASA and previously worked at NASA's Goddard Space Flight Center in Maryland. So what I do is planetary remote sensing. You've heard some other folks talk about remote sensing. In my specific case, what I'm interested in is using satellites to take a certain type of image of both the surface of Mars and the surface of Earth. And that type of image is thermal infrared data. So that's a type of light that tells us information about the temperature of the surface. A lot of what I do and a lot of my extreme environments are related to understanding materials on the surface of Mars. So we take pictures with satellites of the surface of Mars, like I'm showing in this little cartoon here. And then we go to various environments on Earth that we think are similar to places on Mars, and we take pictures of those places, except we can go to those places on the ground and figure out exactly what we're looking at. And in that sense, it's what's called an analog or a planetary analog. And we do a process called validation. So we use those images plus the data that we collect on the ground in order to make an interpretation about what we think is on the surface of places on Mars where we aren't really able to go look at the ground. So what that process looks like is it's kind of similar to a rover. So a rover drives around, it takes data from the surface, it tells us a lot more information than we can collect from satellites. We kind of simulate that same process by using a drone with a bunch of cameras as kind of our satellite. And then we take data from like a weather station or from sediment samples in order to inform those observations. So we've done this work in a lot of different places, and I'm going to give you a few examples. This picture is from a site just in the backyard of where I did my graduate studies in northern Arizona. This was just really close to Flagstaff, Arizona, and it's actually a really good analog for sand dunes on Mars. But I'm going to take you to a couple different places. We're talking about temperature. First, I'm going to take you somewhere that's potentially very hot, and then we'll go somewhere very cold. So one place I've done quite a bit of work is at Kilauea in Hawaii. So part of that work has been to study volcanic landscapes. We have similar volcanic features on Mars as we see in places like Hawaii and also in northern Arizona. I'm going to focus on Hawaii for a second. And this is just an example of some of the satellite data that we might collect from Hawaii. So on the left is kind of what you would see in terms of the colors with your eyes of the Kilauea volcano. You can see where vegetation is or where plants are in green, but where like the lava is, that's all brown and black. Then if we look at that in terms of the temperature of the surface, you can see that those lavas, they also have an elevated temperature relative to the surrounding vegetation. And there's a particularly hot point right at the middle of the volcanic crater here. You might be wondering, why is that spot so hot? Well, this is a volcano after all. This is a really good time actually to be, we have to skip through some ads here to look at this YouTube video. But this is a really good time here to be talking about Kilauea volcano because it's been actually over the last few months undergoing a series of really dramatic eruptions. This is a fire fountain from just a couple weeks ago. And if you want to actually, I don't think the fire fountain is happening at this very moment, but it's been happening sporadically over the last few weeks. And if you can actually go and watch these videos of it in real time, if you go to this link or if you go to YouTube and you can just type in the USGS live videos from Kilauea volcano. But it's these really dramatic eruptions similar to eruptions that we think occurred on Mars in Mars's past. Okay, I'm going to take you now to a very different set of landscapes. We've been thinking about very hot. Now we're going to start thinking about, very cold landscapes. So another set of environments that I've done quite a bit of analog work in and validation work in has been in the Arctic, studying similar processes that you heard about in the last talk, looking at permafrost. And so I had the opportunity last year to travel on a boat for about a month from Iceland to Alaska via this channel called the Northwest Passage through these islands in northern Canada. So we took the boat along the coast of Greenland through these islands and ultimately ended up in Nome, Alaska. There's a set of pictures here. Here's me from the bridge. You can tell it's cold because there's icebergs in the background. We saw lots of polar bears along this journey. But typically what our days would look like is we would pack up all our equipment, like those drones and the weather station I showed you in those previous pictures. We jump on a Zodiac, which is kind of a raft with a motor, and we motor to shore, and then we hike around on shore and find a suitable place to collect data. So this is an image from Greenland. Our green path here is spotted with a bunch of different pieces of information here. Each of these colorful orange-ish boxes, that's actually a satellite surface temperature data set collected at the exact time that our boat was driving through that part of the image. And then each of these turquoise stars are places where we got off the boat and collected data. So I don't necessarily have one extreme environment. I actually have been fortunate enough to visit quite a number of different environments where we've been able to collect this type of ground truth data. And just to highlight some images from a few of those different places, we've been to Devon Island in the high Arctic, looking at these really interesting wedge features that form in permafrost thawing environments. Spent a lot of time in Iceland studying glacial landforms. Here's looking at these conical mound features, like these cones that form in landslide deposits in southern Greenland. And I could go on, but I want to leave time for questions, so I'll just leave it there with this closing picture. We got to wear these fun jackets that said exploration scientist, which really made us feel legitimate during that voyage. So thank you all for giving me the opportunity to talk to you, and I'm happy to chat more about some of the work I've done.
Thank you so much. All right. So we're down to the end here. Thank you all so much. So for questions, we've got time now for questions for Dr. Kirby Runyon. And he's the one who was on the airplane going up and down with the gravity. And we've got questions for Ari, who just spoke about his travels, and questions for Sumitra, who's studying in Alaska and dealing with things, all sorts of wildlife while trying to study the permafrost there. Does anyone in the room here have questions that they would like? Let's go ahead and have all the three of you, if with questions, come on down and we'll have you ask them one at a time, okay? So who is your question for? Dr. Kirby.
Dr. Kirby, is it hard eating food in zero gravity?
Is it hard eating food in zero gravity? I've only I've only ever eaten jelly beans and drank water in zero gravity. But no, it's not hard. What is hard is if it's floating in front of you, to float up to it and actually get it in your mouth, because usually it like bounces off your nose or your chin. Or if you're trying to drink water, it just sort of like gets on your face. But water blobs just sort of like float in front of you like an amoeba, and you have to like, but it's usually floating in some direction, so you have to like kind of chase it and suck it up. Jelly beans are a little easier, and what's fun is you can take the jelly beans and just like toss them at people, and if you got good aim, it'll go right in their mouth. Or if you have like a cloud of jelly beans, you can just kind of float up and eat it. I've seen someone else eat pizza in weightlessness. I mean, your swallowing mechanism. So for astronauts in space, no, eating is the same. It is like your body thinks of it as the same, whether you're in gravity or not. It's just getting the food to your face that can be the tricky part.
Okay, thank you. Awesome. Who's your question for?
So, Mr. Kirby, what inspired on the Planck make of gravity?
If I understood the question correctly, it's how do we make that reduce gravity? Is that right? Yeah. So one experiment you can do yourself is if you take like a 2-liter empty soda bottle and you put like little Lego guys inside, and maybe you screw it on tight, and then maybe you like duct tape some weights on it, like bean bags or something, and that's just to help it overcome air resistance. And then you throw it. It's going to follow what we call a parabolic arc. And that's described by Newton's laws of motion. You can go look that up. You can write down those equations and you can predict exactly how that's going to fly in the air. And if you look carefully at your little Lego guy in the soda bottle, you'll note that he's just sort of like bouncing off the walls. To him, he's weightless. There's nothing that's pulling him. He and the soda bottle are following the same path through the sky, and there's nothing to make him be attracted to the floor of the soda bottle. And so the same way, when the airplane flies up and then it starts to pitch over like that, what it's basically doing is it's launching your body and everything inside the airplane on this ballistic trajectory, just like if you toss that soda bottle. And so it's more that your body is just flying through the air at 30,000 feet, and the airplane is just flying around you as your body is flying. And then when it's time to hopefully not crash, the airplane will pull up, and then it kind of gently catches you from below as the airplane then begins to fly normally, and you gently settle to the floor. So it's the airplane recreates reduced gravity or zero gravity by following the same ballistic path through the sky that a projectile would. And it's actually the same physics of what allows astronauts in space to be weightless, except that they're in a complete orbit, whereas technically we're on a low altitude suborbital trajectory on the airplane. Great question.
So much. Thank you so much. Awesome. Yay. Who's your question for?
Kirby.
Herbie, okay.
So, what do you do for a hobby?
What I have a number of hobbies. I love studying aviation. I've just started studying to get my private pilot's license. I love I volunteer with my church. I hang out with friends. And let's see, my wife and I love to hang out. We watch shows. But we just moved, so right now we're unpacking a lot of boxes for fun.
Thank you. Thank you. So Sumitra, what has surprised you the most about being there and working in Alaska? What have you dealt with that surprised you that you weren't expecting? Anything?
I think every day is a surprise, I guess. Every day is a thing, but I guess animals, I was so afraid of the wild animals. Like we have a campus moose that frequently visits our buildings and kind of goes all over campus. I was just kind of, for me, what surprised me is like how adapted the animals are to humans, so they don't always come and charge you.
Yep.
So
awesome.
So that was only surprising thing for me, I guess.
That the animals are chill. They're not charging at you when you're out there in the field.
Yeah, and also I guess the auroras as well is one of the things. Is kind of, I knew there were a lot of auroras that you could see in Alaska, but I just didn't realize you could see them like from your house. You'd have to go outside in the cold to see them.
Absolutely. Thank you. Dr. Treeman has a question.
Yeah, I've got a question for Dr. Capel. You talked about temperatures and Mars and stuff. I'm wondering, have you ever found any hot spots on Mars, like active volcanoes or hot springs or something?
That's a great question. Thank you. We have not found any active hotspots on Mars, so that's not necessarily the aspect of the extreme environment that we're looking at. We're not necessarily looking for active volcanoes, but we're looking for the kind of remnants, the pieces that the volcanoes leave behind, and we can use the temperatures at the surface in order to figure out what is an old lava flow versus what's just a normal sand dune.
Thank you. It would be pretty wild to find a warm spot on Mars, right? Yeah, that would be pretty wild. We've only got just a couple minutes left. Any final questions from any of our scientists, speakers, or kids for anyone? Does anyone have any final questions? This was amazing. We've got a question for Sumitra. Do you want to come on down and ask it, or do you just want me to repeat it? There's a question here. What do you like most about working in the cold?
Oh, I love snow and ice, so like that's the thing. Being outside in the cold, like my favorite time in Alaska is in the cold. Like like minus 20s and minus 40s. Those are my temperatures. I love just being outside. At those temperatures, like the wind stops like blowing, so it's usually dry. So it's dry cold. It can really get to you, but there's no wind. I don't like the wind in the cold. So
Being nice and cool out there and without wind. I didn't know that the wind didn't blow at those temperatures. That's good. That's good.
well, it blows, but it blows less. Usually, it's kind of stable cold. Usually.
Fabulous, fabulous. I think that's everything. I want to thank all of our speakers from today. Woo! And I know you can't see or hear all of them, but all of the kids from the club here really appreciated this. And for all of our scientists, if I haven't already received your permission to post these, I'll follow up with you and double check, make sure it's okay. But we had a wonderful time. We had several clubs online with us. I don't think they all were able to stick around the whole time. But thank you so much. We really appreciate it. We appreciate any feedback that you have as well and recommendations for the future. Thank you all so much. Have a lovely day. And thank you for being a part of this program. We really appreciate it. Bye-bye, everyone.